Okay, so let's start our class. And now, today we're going to introduce some of the concepts in Unit 3. Okay, so Unit 3, we're talking about a little bit of thermal chemistry. And then we're going to talk about some of the topic with gases. Okay. So thermal chemistry, to be honest, is full of calculation, because thermal chemistry basically is just is based on math. Okay, thermal chemistry is based on math. It's all calculations, all equations. Okay, and also it's all combined with what we just learned, stoichiometry. Okay, yeah. So this is a thermal chemistry. So that's why I'm talking about this is a little bit harder. And the gas, it just talk about ideal gases, and they all involve a lot of the calculations. Okay, so in general, thermal chemistry, most of cases are calculations. Okay, most of cases are calculations. Okay, but there's some concept I would like to introduce to you. Okay, so the first concept is we need to understand so what is called a system and what is called a surroundings. System and surrounding. So system is talking about, okay, so the universe that you observe. Okay, it's talking about the space or the occupation, the area that you observe. So you call the universe. That you observe. So if you to understand this, it's just like, okay, if I want to do some experiment and then I want to observe what happened for this lab. Okay, so what happened for the thermal dynamics in this lab, in this room, and this room will be just a system. Okay, so that is the universe that I observe. Okay, and if you want to talk about some of the liquids inside of this container, and we observe what happened inside of this container, and then the inside of a container is the universe that we observe, and this is what we call the system. Are you clear? So what do you observe, and then that one is called a system. Okay, and then surrounding is coupled with system. So system is what we observe. Then surrounding is the other area that, other than the system. Then the rest of the others is called the surroundings. Okay, so surrounding is rest of other universe. Other than system. Yeah, so this is the first concept. Okay, so the system and the surrounding is coupled. Okay, it really doesn't matter. Okay, if you think which one is the system, then the rest of the other space are all called surroundings. Okay, yeah, if we think this room is the system, and then the rest of other universe, which means it's not just talking about the rest of the building or the rest of the Wichita or the rest of the universe. Okay, yeah, so those are all called surroundings. Those are all called surroundings. So system, surrounding, those two concepts are coupled. Okay, And then we're going to talk about the heat a little bit. Okay, so what exactly is the heat? And when we talk about heat, the heat, usually we're using small q to represent heat. Okay, small q to represent heat. Heat, first of all, heat is one kind of energy. Okay, and we know the energy, right? There's several different type of energy, but heat is one kind of energy. And this energy is not doing anything else. It's only to make the temperature change. Okay, so heat is only to make the temperature change. So that is heat. This energy is used to increase or decrease the temperature. Okay, so generally, if I receive the heat, then my temperature will increase, right? But if I lose the heat, again, the temperature, your body will decrease. Okay, so this is what happens for the heat. And when we talk about energy, there's several different type of energy, right? You have a kinetic energy, okay? So we also now we're going to talk about several type of energy. There's a kinetic energy. The kinetic energy, which is the energy that is used to make some subject move, right? It's the energy that is used to make the subject move. Yeah, force can be the energy. So that is the kinetic energy. And usually when we talk about kinetic energy in chemistry, most of the cases we talk about the gas molecules. So maybe you cannot see the gas molecule. Nobody can see the gas molecule because the molecule is too small, just like the oxygen gases. That's too small. But right now in this room is full of the gas molecules. But those gas molecules actually is not sitting there forever. It's not sitting there. They are constantly moving and moving very fast. Okay, so when we learn chemistry or physics, most of the cases we need to think about those in the micro scale. Okay, so you can think about the gas molecule is just they're moving everywhere. Okay, yeah, they're moving everywhere, and that is why we got the pressure. The pressure, the reason we have a gas pressure on our body, the pressure is because the gas molecule constantly heating you. Gas molecule constantly heating you, so you feel pressure. Yeah, so that's why if you have some fans blow to you, okay, the gas molecule constantly heating you, then you actually be pushed back. That's because the gas molecule heating you. Okay, yeah. If the gas molecule even go faster, then you will got cut. Right? Yeah, that's so no doubt. Okay, so this is the kinetic energy. Okay, that really depends on how much the energy that can move those molecules. Okay, yeah. And then another energy we talk about is the potential energy. Potential energy. The potential energy is talk about the energy that they stored energy that's stored inside of the energy that is stored inside of the object. Not to make the subject, make the object. Okay, so potential energy, just like right now, I'm holding the pen. The pen has the potential energy, right? So you can think about when when I lose the support, it will fall down. So the energy, the potential energy will transfer to the kinetic energy. Then it will move, right? So chemistry also talk about potential energy, but those potential energy is not in physically holding like the pen, okay? It's invisibly holding inside of the bond, okay? Inside of bond. I mean, if you're learn the biology, or we talk about the ATP, right? Yeah, the ATP is storing the energy inside of the bonds between the phosphate. Okay, so when the metabolism, they're going to release the energy over there to keep the metabolism of the bodies. So the potential energy in chemistry we talk about is the energy that's stored in bond. In chemical bond. So that is the potential energy we talk about. But right now, this energy is the heat. The heat is also energy, but this energy is not storing somewhere. It's not making something moving faster. It's trying to increase the temperature. Okay, so that is the purpose of the heat. So heat is a kind of energy that makes temperature change. So in another word, the heat can be transferred. Can be transferred or can flow. Heat can flow. Heat can flow. Okay, so where they flow, they usually the heat they flow from higher temperature to a lower temperature. From the higher temperature object to the lower temperature object. That's really not depends on the size of the object. It only depends on the temperature of the object. If you have a tiny bitty copper unit, okay, but this tiny bitty, it's really hot, right? Then you touch it, you feel hot, and you gotta burn. That's because the heat is transferred from those tiny bitty copper to your body. Okay, yeah, the heat is being transferred from the hot temperature object to the low temperature object. So this is a flow of the heat. In another word, if you open a refrigerator, you feel cold. It's not because the cold air to you. Actually, it's because your heat is being sucked by the refrigerator. Okay, the heat in your body is being sucked. Your body is constantly losing the heat, so you feel cold. Okay, yeah. So that is the reason. We're wearing the clothes is try to prevent the heat be transferred out, because constantly this room is much colder than our body. Okay, yeah. So we wear those, it just prevent the energy being out. Okay, well, but the point is our body temperature is constantly keep a certain temperature. Why? How come? Well, our body mechanism will keep the temperature, certain temperature, but we're constantly losing the heat, right? We're constantly losing the heat to the surroundings. Then what happens? The metabolism in our body digest the food or the fat that's stored in our body. Okay, Yeah, and then can keep our energy up, even we're losing the heat, but we're still keep the energy up, right? Yeah. So that is why you need to eat. Okay, otherwise you will die. Okay, yeah. So this is what happened. Okay, yeah. So heat, just let you recognize the heat is transferred from high temperature to the low temperature. Okay, yeah, the heat will transfer. Okay, so the next part, we're going to talk about another concept, and this is called one of the chemistry is one of the concept. It's called endothermic or exothermic. Exothermic and endothermic reactions. Okay, doesn't maybe not a reaction, but could be a process. Phase change can also make this. The exothermic reaction is, or exothermic process is talking about during this process, we're releasing the heat out. Okay, so this is going to be releasing. In another word, this is a system. Remember, if we assume our body is a system, so the system is going to release the heat and the surrounding will gain the heat. Okay, system release heat. Surrounding gains heat. Okay, so those are the direction is, I mean, generally those two are talking about the same thing. If the system losing the heat, surrounding must gain, right? Because we talk about surrounding heat, surrounding and the system are coupled. Okay, if the system release the heat, then the surrounding must gain that heat because heat cannot be destroyed or generated. Okay, so something release the heat, the something must gain that. Otherwise, the heat is not calculated correctly. So system release the heat, surrounding must gain the heat. That is called the exothermic. Endothermic is go opposite way, which means the system gain the heat and the surrounding is losing the heat.
So it's basically like a flame and then like ice cream.
Then that really depends on what what system you're talking about. Are you talking about the flame or are you talking about the ice cube?
Well, like exothermic would be like a flame. That's
Exothermic, yes, that's a flame.
endothermic would be like ice cream.
Yeah, ice cube, yes, you have an ice cube. If you keep constantly heating it, it will melt. And this process from ice cube to the liquid water, this is the endothermic process because they need to receive the ice cube need to receive the heat. Otherwise, they're not going to change. That makes sense, right? Kira?
I'm thinking about like when I go to like photo, I can't even talk. Like a red light and like cryotherapy. It's like red light, you know, like that heats you up, but then the cryotherapy like cools you down really fast. And it's interesting to think about. Like your body is changing these two.
Yeah. So you see, endothermic and exothermic is a coupled. That really depends on what kind of system you're talking about. Just like the flame and the ice cube. If you're talking about flame constantly giving the heat out, right? So that flame is exothermic. But if you're talking about the ice cube, then this system is become endothermic because it constantly receive the heat, and this is the heat is coming from the flame. right? Okay, so the endothermic and exothermic is coupled together. Okay, coupled together. So let's talk about some of the process, just like okay, Casey's talk about some of the process phase change can be. Okay, what kind of phase change will be endothermic? What kind of phase change will be exothermic? Okay, so so let's think about it. I mean, this one will be tested in the exam. Okay, so be careful. And we only talk about 3 different phases: the gas phases, and the liquid, and then solid. I mean, to think about which one has a higher energy, then you can just think about the temperature. Think about the water. Which one? The gas molecule usually has a higher energy because the gas usually has a higher temperature, right? Above 100 Celsius. Liquid is between 0 to 100, and solid is below 0, right? So solid has a much less energy, okay, compared to the gas and the liquid. Or you think about much less heat, right? Because heat changing their temperatures, right? Changing their temperatures. So that is why everything from gas down, doesn't matter is from liquid, from gas to the liquid, or gas to the solids, or liquid to the solids, everything go down, which means the temperature change decrease. Then those are all you can think about. Is it endothermic or exothermic? What do you think? Page? Huh? I'm talking about, okay, anything the temperature goes down from gas phase to the liquid phase, gas phase to the solid, or liquid to the solid. What kind of a phase change? What kind of is it endothermic or exothermic? It's exothermic because they produce the heat out. The temperature decrease, you see? From gas has a high temperature, then to the liquid has a lower temperature. So temperature decrease, obviously you're releasing the heat out.
So when sublimation occurs, it's like a drastic, like gas.
Sublimation go backwards. Sublimation from solid to the gas. Then this process need heat, because you see heat has higher energy. So they need to absorb the heat to do the sublimation. So everything go up from solid to the liquid and to the gas. Everything goes up, and remember, they need energy, they need heat. Otherwise, they cannot reach to that certain temperature, right? So once everything goes up, goes down is exothermic because they are releasing the heat. Goes up, this is endothermic because they need heat. Okay, in another word, when you boil the water, this is a process of endothermic because the water need to keep constantly got heat, right? Then the reach to the higher temperature, then making it boil, right? So boil water, which is from liquid to the gas phase, and this is all endothermic process. So those are, if you're from gas to the liquid, and this is what we call the condensation. This is exo. From gas to the solids, this is called deposition. And from liquid to the solids, this is called freezing. So those processes are all exothermic. And the other half, from liquid to the gas, this is called vaporization. And from solid to gas, this is called a sublimation. And then the last one is from solid to liquid. and this is a melting. So those processes are all endothermic. It's an endothermic process, and this is an exothermic process. That makes sense, right? So, and then, so that's why I want you to make a connection between endothermic and exothermic. Okay, yeah, endothermic and exothermic. Yes. So endothermic, exothermic, that's the whole process. Well, this is a phase change. Phase change is not a chemical reactions, but in the chemical reaction, they also have similar things. Okay, yeah, some of the chemicals can be exothermic, like if we talk about the chemical reactions, like combustion reactions. Combustion reactions, they are the exothermic for sure. That's the exothermic reactions because we're producing heat out, right? So everything you gotta burn everything. This definitely is exothermic. Okay. Endothermic for the chemical reaction is very subtle, not easy to be observed, but we do have a lot of endothermic reactions. I will let you to watch one of the demos. And endothermic reaction is subtle, not very obvious. Okay, so let's looking at one of the endothermic reactions.
You don't supposed to do, and somehow it all just comes together. And then you don't know why you wouldn't have.
What I have is some barium hydroxide. Okay, and I'm going to put this into the. In fact, you know what? I'm going to do this in one of the beakers, not that thing, because it's ridiculous. Barium hydroxide, and I've got some ammonium chloride. Now, what I'm going to do is mix these together, and hopefully we should see a endothermic reaction. Yes.
It's with the hand stuff.
What hand stuff?
The hand sanitizer.
Oh, it just lives on my desk. I was chopping up hearts earlier, and yeah, I need to be not covered in blood. So, what I'm going to do to show how exothermic this is, how much heat this is taking in, I'm going to make this wooden block wet. Okay? Now, you will see why I've done that in a second. So, I'm going to mix these two things together and carefully. In fact, I need to break that up a bit. Mix these two things together. Well, hopefully not, because if it's blowing up and giving out huge amounts of energy like that, that would be what type of reaction? Exothermic. Now, we want to see endothermic, so it's going to be a little bit more subtle. So, I mix the barium hydroxide and the ammonium chloride together, and they should start to react.
Does it freeze it?
Well, we should soon see. So they're mixing together. Now, can you see how the consistency of that is changing slightly? It's sort of clumping together, because one of the products it's making is water in this reaction. And you can see actually that's all gone liquid, and it was all just solid powders. It's not milk. You wouldn't want to put it in coffee. Okay, if you put that in coffee, there'll be problems. Now, one of the products of this, because it's ammonium chloride, is it's giving off ammonia, which smells rather horrible. And I'd forgotten about that, which is why I just breathed the huge load in. That sort of horrible, slightly tangy smell in wee is sort of ammonia-like.
Oh, is that what I can smell?
Yeah, that's what you can smell. Unless you've wet yourself, that is the best smell you can smell. Okay, but also, actually, this is getting actually very cold as it's going along. Okay, now hopefully, if this has worked, it's getting cold enough. Well, you know, I put water on the base there.
Yeah.
Fingers crossed. It's actually frozen the water onto the bottom. Now, this reaction has worked so well, so much energy has had to be taken out of the environment. It's got that water so cold that it's dropped below freezing and frozen onto the bottom. And that is pretty cool.
How cold is it?
Well, I haven't got. In fact, I have got a thermometer. I'm an absolute liar. So I can put that there. That is dropping down to. Well, we know it's below what? 0. So
Freezes it to.
this thermometer is calibrated to -10. It's shot down to -5 by about now. And it's carrying on going.
Will it freeze our fingers?
Okay, so this is a typical endothermic reactions. Okay, so then we can think about the system over here. I mean, why this is an endothermic? Okay, the endothermic over here. So we have a bottle, right? And we put a wood block over here, and then we put the water in between this, And remember, endothermic is compared to the reactions. So we're having the chemical reactions over there. The chemical reactions shows over there. Then this chemical reaction is the endothermic chemical reactions. In other words, they're going to absorb heat, right? They need to absorb heat for this reaction happened. So they need to absorb heat. Then where's the heat? If we think about this as a system, so the rest of the others, like this, the rest of those are all called the surroundings, right? So if the heat, this system absorbing the heat, then that means the surrounding is going to losing the heat, right? The surrounding is going to losing the heat. When the surrounding losing heat, then what happens? The surrounding going to decrease the temperature. The temperature will going down, and then since we have a water up there, when the temperature down for the water become ice, and then they're going to glue them together. So this is what happens for these reactions. So that's telling us this is endothermic. So that's why some of the reactions, if you do the reactions, then you will see, oh wow, the outside is really cold. Then this is telling us it's endothermic. But just to let you know, most of the reaction is the exothermic reactions. For example, when we dissolve sodium hydroxide, or we dissolve the acid in a water, then if you touch the glass in the outside, you feel warmer. Yeah, that's because when they dissolve the sodium hydroxide or HCl dissolve in the water, they actually is exothermic reactions. They are producing heat out. Okay, that's it. So this is a endothermic and exothermic. Hopefully you still understand this way. And remember, endothermic is a system gain the heat and the surrounding lose the heat. And exothermic is a system lose the heat and the surrounding gain the heat. Okay, so this is what happened. Okay, let's take a break, and then we will come back for another 20 minutes. Then we will done for today's lecture. Okay, yeah. What? You don't want to have a break?
Oh, yeah, it's in the break.
Are you sure? Okay. Okay, let me grab. Oh, by the way, I completely forgot it. We need to turn in the lab report. Okay, so now there's a 2 lab report I'm gonna turn in, right? Lab 90 and lab 95.
You never told us a few other questions.
Really?
Listen, the report. I'm working on it. So it's gone. That was the other people. But no, hurt.
Okay, so I think it is 63, page 63 for the lab report. Yeah.
Because I have 90 now. I didn't.
Lab 95, the free lab president is 60, page 63. Huh? We already turning lab report.
Page 63.
Huh?
We like page 63.
Okay, that's great, for the 95.
Yeah, you never
Well,
told
now
us.
you can turn in the lab 90,
Okay.
okay, you don't have to turn in the 95, lab 90.
We can help them say it. I have my own room. I have a careful, yes. Yes. So in Peter Pan. There's a lady that Peter Pan. I had the most chicken in my room. I have an emergency exit. My room that had the most chickens escape. Like, fuck this bitch is fucking creepy. I'm out of here.
I literally thought you meant like actual chicken. And I was
They
really.
were. Literally.
I was like, what is she talking about?
It was pretty great.
You guys know?
Yeah, Lady Peter Pants in the butcher room. He was wearing someone else's skin on his face. It's called 13 Sinister Souls. Good, I'll be there. I'll be there. I'm in the abomination. You won't even, you're like, oh, you're not terrible, you should.
Come back to all time.
I'd love to live in that. I would have to love to be so happy to live right. This baby. So good. I just need to recuperate so I can lose it again.
Yes. Or just actually talk like that. I'm not scared you're on.
No, I want to get with the jet.
Left 90, just 1190.
They're just playing.
Yeah. I never heard it. Oh, we said yes. Oh, you want?
Did you realize that we already agreed the left 1190, 1120?
Did.
We agreed the left 20. We agreed the left 20 for the other people.
Oh, that's right. No, maybe I can. I don't think I can.
Probably did. I'm just like ready to
Hey,
Oh, yeah,
guys,
Wait,
95.
we did have to fill out questions.
We do have.
I know.
It's only to lab, like,
It's on the model.
yeah, if you go to like the lab.
But that's okay. No, we don't have a lab for today. Okay, no lab for today. Okay, so the next part, I would like to, to understand the endothermic or exothermic. Let's talk about some of the cases, and then you can think about whether this is endothermic or exothermic. Okay, first of all, already mentioned, we're boiling the water to gas phases. For the water, is it endothermic or exothermic? It's endothermic, right? Yeah. So we're pan fry a chicken. Okay, for the chicken, is it endothermic or exothermic? That's gonna be endothermic because the chicken is getting fried, right? So it has you need to heat it up, right? So the chicken receive the heat, okay? And we're burning a wood, and to the wood is endothermic or exothermic. We are burning a wood. For the wood, is endothermic or exothermic process? This is a very confusing because you see, you're burning a wood. Is the wood receive the heat or release the heat? Wood release the heat because they burn the heat, burn the wood. Wood is burned. They release the heat out, and then you see what's the leftover for the burn? Wood. It's the ashes, which means the energy are gone. All the energy are released out. That makes sense, right? So this is the exothermic. But you're standing out, I mean, surround, you're stand, I mean, just a bit, I mean, close to the wood. For you, what happened? You receive the heat, you feel warm. So you're, as a system, you are endothermic process. This is endothermic process. That makes sense, right? So system, when we talk about endothermic or exothermic, they really depends on what's the system you are talking about. That makes sense, right? Yeah. So this is generally helping you to understand what is endothermic, what is exothermic. Okay, endothermic and exothermic. So the next part we're going to, okay, since we talk about endothermic or exothermic, and we're going to, they have a directions, right? Release or gain, release or gain. So when we talk about, exothermic, we always, the heat is a negative heat. Okay, as the heat has a sign. I mean, usually heat don't have a sign, it's just energy. Energy don't have a sign, but the sign is talking about the releasing or gain. Okay, exothermic has a negative sign, then that means it's releasing or lost or lose. That's because they talk about system, right? We talk about system losing the heat. So that is why they have a negative sign shows up here. The negative means it's release or loss, lose. That makes sense, right? And then the endothermic, then they just go opposite way. Endothermic has a positive number, which means this is a gaining or add. Okay, that's because they need to, the system need to gain the heat. So the heat for the system is gaining. So that's why we have a positive sign. But just to let you know, right now you're pretty clear about this. But 2 days later, this coming Thursday, when I talk about, you're gonna confused. Okay, yeah. So that's why we need to constantly repeating. I mean, what's going on over here? Okay, exothermic and endothermic. Are you clear? Exothermic and endothermic over here. And also they have a sign. The next part, we're going to talk about the unit of heat and and also the unit conversion for the heat. Unit of heat. So usually the SI unit or the scientific units, that's using a joule. Using joule or capital J. Okay, joule is a really small unit, and usually we're not using the joule. Instead, we're using kilojoule. Okay, which means 1,000 joule. This is a common unit that we're using. Okay, this is a common unit we're using. And also, I need to, I hope you realize there's another 2 units. It's called a calorie and a kilocalorie. Pascal is the pressure. Okay, calorie and a kilocalorie. I bet you definitely remember, recognize this, okay? So every time when you eat the snack, the label shows you don't eat it, it's gain the heat. Okay, you're gain the energy. It says, how much you eat for this. Maybe it's just small chocolate, then you eat 200 kilojoules over there. Okay, no, 200 calorie. But that calorie is not this calorie. It's talk about is a kilocalorie. Okay, so kilocalorie is also called a food calorie. Okay, kilocalorie is also called a food calorie. It's a much bigger units when we talk about this calorie. This small calorie is just a calorie, but usually we're not using that. This is the common unit that people recognize. We also call it as a kcal or food calorie. Okay, so a human body usually every day average is about like a 2,000 to 3,000. I mean, adults we talk about 2,000, 3,000 kilocalorie, or we talk about food calorie. This is pretty much just a very tiny bitty chocolate can like a 200. Okay, so you see, and if you're looking at, I'm not sure whether you're looking at for Coca-Cola, one tin of Coca-Cola, how much? We can search, we can find it. $150 calories. 150 calories. Okay, yeah. So that's a lot. Actually, there's a lot of sugars inside. Okay, if you know how to make the Coca-Cola, then you probably don't want to eat it, want to drink it. Okay, one small tin of the Coca-Cola, you probably is gonna add a similar size of the sugar inside of that.
You know, it used to be in Coca-Cola.
Yeah. That's a lot of sugar. That's a lot of sugar. You know what? A lot of cakes, the pound cakes, okay? The very tasty cake, they definitely has a much more sugar and fat in there, okay? You can taste just a little bit, don't eat too much, okay? Yeah, so everything you can eat, but don't eat too much. That's it, okay? Oh, anyway, so this is the unit of the heat, okay? This is the heat we're talking about. And the next part, we're going to talk about a temperature unit, right? The temperature unit. I think I bet you already know this. Temperature units, they are including 3 units, right? Celsius, Fahrenheit, and Kelvin. Kelvin is a capital K, okay? So what is the difference between those? Then I'm going to just draw 3 bars over here, and then you probably will recognize. So first, Celsius, let's first see Fahrenheit, Celsius, and Kelvin. Okay, so for the freezing point of the ice, what is the Fahrenheit? 32, I think, right? 32. So that's a 32 Fahrenheit. How about the boiling point of the water? 212, right? It's a 212. How about the body temperature? 97 something, right? Let's just say 98. Let's just say 98, okay?
Internal body temperature.
I'm not a nurse or doc, so I don't know. Okay, I just using 98. Okay, so and you know the Celsius is a 0, right? It's a 0 for freezing point of the water and 100 for the boiling point of the water. So actually, this is 0 and 100 is actually defined by the water. They just define the water is 0 Celsius for the freezing point. of the water, and the boiling point of the water is 100 Celsius. This is how they define the Celsius. Okay, so the Celsius generally is based on the temperature of the water and the water. The body temperature we talk about is about 37 or 30, a little bit 36, 36 point something, okay, 0.8 something. So this is a close number. And for the Kelvin, the zero is 273, okay? Actually, it's a 273.15, but usually I just using 273, okay? And the 100 Celsius is a 373. And the temperature over here, 37 plus this number is like a 310. So this is a Kelvin. This is Kelvin, okay? So you can see the Celsius and the Kelvin, the only difference is 273, okay? So 273 plus the Celsius, then you will convert that unit. A Celsius number, you plus 273, then you got a Kelvin. Okay, so this is conversion. And those are all have a zero, but there's a zero for the Kelvin, then this is called the absolute zero. Absolute zero is the ideal temperature, which means there's no such temperature can reach to absolute zero. There's a temperature really close to zero, but never got exactly absolute zero, okay? Because by definition, absolute zero is during that situation, nothing will active. Even the small scale, even the atom is all freezed, it's all frozen. Okay, atom is all frozen, nothing can move. And that's a certain point, that's called absolute zero. So how come we can detect that temperature? Because everything is frozen, even the electricity, even the electrons are frozen. Then there's no such, instrument can detect that temperature. But we can have another way can predict, and then there's an absolute zero for sure. Okay, yeah. So then for Celsius, the temperature absolute zero is a negative 273 Celsius, and for Kelvin is a negative 460. I think it's a negative 460. It's really cold temperature. It's really cold temperature. So that is the difference between this. I don't care about how you convert between Celsius and Fahrenheit because we're not testing that. But you do need to understand how to convert Celsius to Kelvin. The Kelvin is equal to Celsius temperature plus 273. That's it. Celsius temperature plus 273. Then you convert that to the Kelvin. That is. Okay. So generally, this is pretty much we talk about for today. Okay, and then we're going to talk more in the next class.